Hey there, welcome back. We're going to work some more on molar mass today. Today we're dealing with the concept, God, I can't even talk today. The concept of molar mass as it applies to compounds. So far we've only been dealing with molar mass and Avogadro's number as it dealt with elements. So today we're going to be working on a little bit more complex kinds of things. So this is that time that if you've been putting off learning how to do names and formulas or remembering how to do all your polyatomics or balanced charges or use parentheses, it's time. I'm sorry, but it's time. Anyway, so today we're, like I said, molar mass and how to do molar mass with compounds as opposed to just elements. So again, the big picture that we've been working with, that we're building the last couple of lessons here, has been about how to use Avogadro's number and how to use molar mass. So our two big conversions that we have is that 6.022 times 10 to the 23rd items is a mole. Again, that's called Avogadro's number that we use only if we're trying to figure out numbers of atoms or numbers of molecules, and that's what we'll do today. And then the second big concept is the concept of molar mass. And molar mass is the mass of 1 mole of an element, and it's that mass from the periodic table or the atomic table mass. Average atomic mass in grams, there you go. These two concepts also work for compounds. So they work for things where we've got more than one element present, as well as they work for atoms or different elements by themselves. It's just one extra little step to it that you'll see really isn't all that difficult. So, for example, if we're talking about moles of water, and in this particular case, we'll start off with a simple one, H2O. If we've got 3.75 moles of water, how many water molecules are present in there? And then part two will be how many atoms of hydrogen would be in there. So let's take a look at how we take this problem apart. So how many water molecules would be in here? We're going to take a, oh, my circle got off. That's supposed to be on molecules. Anyway, we're trying to convert from moles to molecules in this case. So what does this look like? Here's our little one diffraction, our little dimensional analysis. We're going to start off with moles, and just like we've done before, now we're going to put moles on the bottom, and we're going to use Avogadro's number to convert from moles to particles, to items. But in this case, the particles or the items that we're talking about isn't single atoms, it's actually the little clusters of atoms that we call molecules. So we would use Avogadro's number here, but not moles to atoms, we're going to use moles to molecules. So if we're dealing with compounds, same exact idea like we've done before. It's just that we have a slightly different unit here. And that unit is that we've got 6.022 times 10 to the 23rd molecules of water, as opposed to, we can't have atoms of water, that doesn't make sense. So when we do this calculation that's on here, here's how it turns out. Again, we have to round it to our correct number of sig figs. We've got 3 sig figs going in, 3.75. So our answer coming out would be 2.26 times 10 to the 24th molecules of water would be in that many moles of water. So that's no different. We can then take it one step further and figure out how many atoms of hydrogen would be present in here. This is part 2 of the problem. Well, think about what's going on in an in a molecule of water. A molecule of water has H2O in it. It's got 2 atoms of hydrogen and 1 atom of oxygen for every molecule. So you can see what I've done here is I've sort of set up a little extra conversion step that we can do that shows us that there are 2 atoms of hydrogen in 1 molecule. You can just set it up like a little conversion factor. Basically all you're doing is multiplying your answer by 2, the number of atoms of that particular element in that particular compound. So in this case, we'd simply multiply by 2, 4.52 times 10 to the 24th atoms of hydrogen. So again, all you're doing is then taking that molecule apart to give the number of atoms of that individual element. So big idea here. When we take a look at this kind of in summary, right? The molar mass of an element is the atomic mass of that element. The molar mass for a compound, this right here should say molar mass for compounds, should be the mass of all of those elements added together. Again, the thing you've got to watch out for here is to make sure that when you're adding those compounds up, is that you need to be looking at dealing with the different elements that are present. So watch out for subscripts in there. So like in H2O, when I want to find that, I would have to add the molar mass of hydrogen twice. So let's take a look at an example of how we would apply that. Again, sorry for my typo on here. This word here should be molar mass for compounds. So what is the molar mass of magnesium bromide? So you have to start off with, first of all, writing the formula. So this is that part where, you know, the rubber kind of meets the road on Unit 4. Did you actually remember how to do all this stuff? So here's how I would start. Magnesium and bromine. Magnesium has a charge of 2+. Bromide means it's bromine by itself as an ion, so it's Br1-. It's not a polyatomic in this case. And then I have to cancel, cross my charges down to get the formula of magnesium bromide. There it is, MgBr2. So now when I want to figure out what the masses are that's involved with this, magnesium weighs 24.305, and I just got that directly from the periodic table. That's the molar mass of magnesium. For bromine, Bromine's molar mass is 79.904 grams per mole, but then I have to remember to multiply this by 2. Because there are 2 bromines in each magnesium bromide molecule, it's not really molecule, but close enough, I would have to multiply that, and I get my final answer by the time I add all those up. It's 24.3 plus 79.9 plus another 79.9. Total mass here is 184.113. Again, the rule in my class, typically if you take it to 2 decimal places, that will be enough, so you could use it as a 184.11 and that would work. But that's how you'd calculate out molar mass for compounds. Again, it's the same idea. Just break it apart. Which elements are present? How much does each atom of each element weigh? So here's one for you to kind of work on. It's a polyatomic. Of course, I had to give you an evil one. I did the easy one myself. I'm going to go through and work this out myself, but this is that spot that if you're pretty comfortable, this is where you hit pause and see if you can kind of work it out, kind of struggle your way through it, and then you know I'm going to do it here in just a second anyway. So this one is, what's the molar mass of titanium 2-phosphate? So it's a polyatomic and it's a type 2. Right? Oh, God. Yeah, so get your periodic table out. Go figure out what these things are. Like I said, I'm going to go on right here, so if you want to challenge yourself, now's where you hit pause and you do it. I'm going to move on. Okay, titanium 2-phosphate. First thing first, write the formula of the compound. Titanium 2, remember that Roman numeral 2 means that it has a charge of 2, so I have titanium 2 plus right here. That's what that little 2 right there comes from. It's the charge, not the number. There's no subscript 2 here. And then phosphate is PO4. And again, don't forget, you have to make the charges of those things in there as well. Phosphate is our 3- that we have. So now we're going to write the final formula. It's symbol charge, cross them down. Yay. To do our final thing, there it is. We had to make that titanium 3, PO4, 2. And again, it's because that's the way that the charge is crossed down to get our complete formula correct. So this 3 becomes the subscript on the titanium. This 2 becomes the subscript on the phosphate. And you can see I've got my parentheses around there to make that kind of hold together. So now we can start kind of attacking the molar mass. And it's just the molar mass of each thing, and then don't forget your subscripts. So kind of working our way through. Titanium, it has a molar mass of 47.867. There's 3 of them, so I'm going to multiply that value by 3. Phosphorus has a molar mass of 30.794. Again, that's just right from the periodic table. And now there's 2 of those. Again, this number 2 out here distributes across. It goes to the oxygen, but it also goes for the phosphorus, and that's why I have this 2 down here. And then for the oxygens weigh 15.9994. And then that's for right off the periodic table. And then the total number of oxygens I have is 8, actually. There's oxygen times 4, and then times 2 again. So don't forget both of those in there. So you can just say times 8 is fine. I'm just putting those numbers out there so you can kind of see where they came from. So by the time you enter all this craziness into your calculator, you should be able to get the answer of 333.181. And again, double check to make sure that you're entering it correctly. If you did not do this and get the same answer, try again. It's probably a subscript issue in terms of dealing with, the parentheses or how you're entering in your multiplication on your calculator. Okay. How do we use this? So now we can do conversions from molar mass. Now that you know how to calculate molar mass of compounds, doing these kinds of problems is very similar to the ones that we've done in the previous lesson, where we're simply converting from grams to moles or moles to grams. It's just now our molar mass is slightly larger than it would be otherwise. So here we go. How many moles of ammonium nitrate are there in 92.35 grams of ammonium nitrate? So again, same idea. If you were pretty good at this, this is where I would hit pause if I were you, go through the steps and see if you can figure out what it is, because I'm about to work this out myself. Are you ready? Are you sure? Ammonium nitrate. Start by writing the formula. Ammonium nitrate's a polyatomic. Oh, moles to grams. Yeah, I know I'm going to do that. Grams to moles needs molar mass. Everything we're going to do needs molar mass. You might as well just get used to that. So here we go. Ammonium nitrate. Ammonium is one of our polyatomics. It's NH4 with a +1 charge. Nitrate, ATE, is also one of our polyatomics with 3 oxygens to it, and it has a 1- charge. So when I write the formula for this, the formula is NH4NO3. So that's the correct formula for ammonium nitrate. Now we can start working on doing our molar mass steps. Since we're doing the grams to moles, you know you're going to need it. So here's how I would do the molar mass. This is the molar mass of nitrogen times 2. It's kind of sneaky, but there's 2 nitrogens in here. Here's 1, and then here's the other one. So there's 2 of those 14s that we need. Plus, this is the molar mass of hydrogen, 1.008, and there's 4 hydrogens in there, and that comes from that subscript right there. And then the last one is oxygen. So oxygen's 15.999, and I've got 3 oxygens that are present, and that comes from that subscript right there. So Again, if you're doing this with my classroom rule where you have to use 2 decimal places, you may have a little bit less than this, but that's okay. Doesn't matter a whole bunch in here what we're doing. So by the time you add these together, our total molar mass from ammonium nitrate to 3 decimal places in this case is 80.043. Now we can do our Wonder fraction. Yeah, get our Wonder fraction set up. We're going to do our dimensional analysis starting with 92.35 grams. So there's our grams from our problem. Now we're going to use our molar mass step. That's what that is right there. And that's the number that we grabbed from above. So molar mass of NH4NO3 is 1 mole of NH4NO3. Again, that's just a molar mass step. And then you can do calculating it out. And there's your final answer. Rounded to the correct number of sig figs. We have 4 sig figs in this problem because our number 92.35 has 4 sig figs. So there's your correct answer, 1.154 moles of ammonium nitrate. Again, really not a lot of difference. The biggest difference here is in the molar mass step. You have to do that addition kind of step first. You got to write the formula out, figure out all the components of that formula, and then add them all up. Okay, I think this is the last one. How many atoms of rubidium are present in 5.75 grams of rubidium sulfate? It's kind of an evil question. There's a bunch of steps to this one. So again, if you're good at this, go ahead and take it apart. If we're dealing with atoms again, taking a look at that, right? How many atoms do I have? And then how many grams do I have? I'm going to have to do a couple of steps. I cannot go from grams to atoms directly. So if I've got grams in there, I'm going to need to go grams to moles. So there's a molar mass step involved. And if I have atoms involved, that means there's got to be an Avogadro's number in there somewhere. And there's actually another step as well. So see if you can figure out what it is. Okay, starting it off. Yep, got to start with the formula. You know you're going to have to do molar mass, so you might as well just start with the formula. So make sure that you figure out where rubidium is. If you haven't found it, it's on the bottom left of the periodic table somewhere. Rubidium is a +1. It's an alkaline metal. Sulfate is one of our polyatomics. So again, sulfate's SO4 with a 2- charge. So by the time we finish writing our formula out, there it is, Rb2SO4. Again, you got to take the coefficients, the charges, and cross them down to become subscript numbers. So that's why we did that crossing down piece. Rb2SO4 is rubidium sulfate. So now we can do our molar mass step. There it is. Rubidium is 85.468. There's 2 of them because it's Rb2. Plus this is the molar mass of sulfur, 32.066. Plus we have then oxygen in there, 15.999, and there's 4 oxygens present. So no parentheses, so we don't have to do any additional multiplication in there. It's just the coefficients that become those multipliers. We find our molar mass of rubidium sulfate is 266.998 grams per mole. All right, so doing our conversions, what do we need to do here? So we're going to start with our first step. Start with what we got, 575 grams of rubidium sulfate. So what do we need to do next? The next step is to do that grams, cross it down, and if we've got grams on the bottom, we're going to have moles on the top. It's going to be our molar mass step. So that's where we're going to use our molar mass of rubidium sulfate. 266.998 grams is 1 mole of rubidium sulfate. Well, now what? Now I'm in moles of rubidium sulfate. And eventually I need to get to atoms. So if I'm going to go to atoms, that means eventually I'm going to have to use Avogadro's number. Here it is. So Avogadro's number. So if we're doing this with compounds now, remember Avogadro's number is 6.022 times 10 to the 23rd molecules of something is 1 mole of that same thing. So there you go. Is how we use that particular piece in there. So there's our Avogadro's number. But if you look at the original question asks you about atoms of rubidium. So how do I do that part? Well, there's one more step. How many atoms of rubidium are in each molecule of rubidium sulfate? Well, there's 2. 1 molecule of rubidium sulfate, there it is right there, that's what it looks like, has 2 atoms of rubidium in it, so there's my last little piece right there. And I can do this all as one giant calculation problem. By the time I enter it all in and round it to sig figs, my final answer is 2.59 times 10 to the 24th atoms of rubidium. So this is kind of everything. This would be the hardest kind of problem that you'd have to do with this sort of thing, where you've got molar mass, you've got Avogadro's number in there, and then you have to remember to take the molecule apart to get to the number of atoms in there. So again, big picture, same thing. I just flipped it upside down for something different. Here's our happy mole right here in the middle. If you're going to do molar mass, grams to moles, that's where you're going to use molar mass. Again, that's from the formula and then from the periodic table. If you're going from moles to molecules like we did in this one, again, that's going to be Avogadro's number. And then if you did that one last step where you're trying to do molecules to atoms within that molecule, then you might use the subscripts from the chemical formula to figure out how many atoms are in there. So there you go. Good luck with these kinds of problems. They can get a little bit long, but remember, get the big picture. Molar mass and Avogadro's number. When do you use them and when do you not use them? Okay? So good luck, and I will see you in class tomorrow. We'll be doing some more labs on this stuff. Ha ha ha. Good luck, right? By the way, I hope you didn't die from all those terrible puns, right? They were awful. I know. Too bad. See you tomorrow.